Hello, future RMTs. Welcome to our second recorded lecture. In this lecture, we're going to discuss laboratory mathematics. I know this will be easy for you because this will be a review of what you had during your inorganic chemistry days and in your analytical chemistry days. But for the purpose of this discussion, we're going to review what we had in the past. This is continuation of what we had in our first recorded lecture. Today, we're going to focus on the most commonly methods or calculations that you need to perform in the laboratory. And one of our learning objectives for this topic is to solve laboratory problems by applying correct formula and derived formula from the mother formula. Alright, to give you a quick overview of what we are going to have in this lecture, we have here logarithms, concentration, specific gravity, as well as conversions. To start with, let's start it with logarithm. Logarithm is defined as the inverse of exponential functions and can be related as x is equals to a raised to b or b is equals to log a times x. This is then read as b is the log base of a of x, where b must be a positive number. A is a positive number and a cannot be equal to 1. Calculators with the log function do not require conversion to scientific notation. To determine the original number from a log value, the process is done in reverse. This process is termed as the antilog. Most calculators require that you enter the value used in inverse or the secondary shift function and enter log. If given of the log is 3.1525, the resulting value should be 1.424 times 10 raised to 3. Let's now apply logarithm in this concept. For example, what will be the pH and the pOH of an unknown substance if the hydrogen concentration is equals to 2.0 times 10 raised to negative 4. I want you to remember, guys, that pH is computed based on the concentration of the hydrogen in a solution. Thus, we said pH is equals to the concentration of hydrogen in a solution. Okay? Remember that pH is the concentration of hydrogen in a solution. Are you wondering why the P in the pH is always written as italized? Or what does the P means? The P means inverse logarithm of or negative logarithm of. Now, how are we going to get the pH? pH is computed as pH is equals to negative log of the hydrogen concentration. How about the pOH? pOH is defined as the concentration of our hydroxide ion. Okay? If pH is defined as the concentration of hydrogen ion, our pOH is defined as the concentration of our hydroxide ion. Thus, we said pOH is equals to negative log of hydroxide concentration. In the problem, we have here the value of our hydrogen concentration is 2.0 times 10 raised to negative 4. We said that our hydrogen concentration, according to the problem, is equals to 2.0 times 10 raised to negative 4. Okay? How are we going to compute for that? Please get your calculator and repeat and do what will I say. In order for us to take the pH of this unknown substance or unknown concentration, you have to input negative log 2.0 times 10 raised to 4, raised to negative 4. Sorry. Again, please input negative log times 2.0 times 10 raised to negative 4. This will give you a value of 3.99 or 3.69, or simply we can say that this is equivalent to 3.70. Now, the pH of a unknown substance with a hydrogen concentration of 3.0 of 2.0 times 10 raised to negative 4 is 3.0, meaning to say the pH, okay, the pH is set at 3.70. Now, how are we going to get the value of our pOH? Remember guys that pH plus pOH is equals to 14. Do you still remember what you had in your analytical chemistry days? We said that Kw, or the constant ionization of water, is equals to the concentration of your hydroxide times the concentration of your hydrogen. The constant value of OH is 1.0 times 10 raised to negative 7. The same thing with the hydrogen concentration. The constant value is 1.0 times 10 raised to negative 7. Meaning to say, this will be 7 and 7. Okay, 7 plus 7 will give us 14. Okay, 7 plus 7 will give us 14. Or simply 1.0 times 10 raised to negative 7 times 1.0 times 10 raised to negative 7 is equals to 1.0 times 10 raised to negative 14. Now get the logarithm or the negative logarithm of 1.0 times 10 raised to negative 14, and this will give you 14. Meaning to say, the pH, the constant pH or the pH of a pure water is 7, and the pOH of pure water is 7. Because again, this is the constant value of your hydrogen and your hydroxide in the constant ionization of water. Having said that pH and pOH is equals to 14, the sum of pH and pOH is equals to 14, then what will be the value of our pOH? If our pH is 3.70, what will be the value of our pOH? Simply, we will get that by subtracting 3.70 to 14. So we have 14 minus 3.70. This will give you 10.3. Okay? Now, we have to identify if our substance is an acid or basic. We all know that if the pH of a certain compound is set at less than 7, we said that it is acidic. Again, we said that if the pH, okay, again, if the pH, no, if the pH of a certain compound is less than 7, then we said that it is acidic. If the pH of a certain uh, substance is greater than 7, then we said that it is basic. And if the pH of a certain compound is equals to 7, then we said it is neutral. Now, having said that this is our reference, now let us discuss or let us define or classify if the pH is acidic or basic. Since it falls to less than 7, then we can say that the pH of this unknown substance is acidic. The question is, how about the pOH? How can we say that a substance is acidic or basic based on its pOH? So simply we have if the pH, I'm sorry, if the pOH of a certain compound is greater than 7, then it is classified as acidic. If the pOH, no, of a cert, I'm sorry, it's pH. Let me correct it. This is pH. Okay. Again. Yeah, it's pOH. Oh my God. Thank you for correcting me. If the pOH of a certain compound is equals or greater than 7, then that is acidic. If the pOH of a certain compound is less than 7, then that is basic. And definitely, if the pOH is equals to 7, then that is neutral. In other words, 10.7 is considered as acidic. Okay? 10.7 is equals to acidic. That's how we compute for the pH and the pOH of a certain compound. Again, remember that the pH is the concentration of hydrogen ion in a given compound, and pOH is the concentration of hydroxide rather in a given concentration. So please do not forget that pH and pOH is important in chemistry. The next concept that we are going to discuss is about percent solution, which can be expressed as weight per weight, volume per volume, or weight per volume. Remember that percent concentration is determined in the same manner regardless whether it is expressed as weight for weight, volume per volume, or weight per volume. Percent implies parts per 100, which is represented by a percent sign, and is independent of the molecular weights of the substance. Meaning to say, the important things to consider in percent concentration is the weight of the analyte, the weight of solute, and the weight of solvent, the volume of solute, the volume of solvent, the weight of the solute, and the volume of solvent. Now, let's have an example. How much sodium hydroxide is needed to make 1000 ml of 10% solution? Guys, take note, based on our definition, we said that percent concentration is independent of the molecular weight of the substance, meaning to say we don't need to get the molar mass of sodium hydroxide. but we are going to compute it in this way. Since we are asked to compute the weight per volume, we are looking for the mass of sodium hydroxide that should be diluted in 1000 ml to make 10% solution. So how are we going to solve for that? Remember, percent concentration, no? Remember that percent concentration is equals to mass of solute over volume of solvent or solution. Remember that in this problem, we are going to look for weight, okay? Weight per volume. Going back, so our volume is, the volume is 1000 ml. The percent concentration in terms of weight per volume is 10%. So how are we going to solve for this? So we have here 10% is equals to x over 1000 ml rather. Okay, x over 1000 ml. So we multiply both sides by 1000 ml. 1000 ml. This will be cancelled. This will be cancelled. X is equals to 1000 ml times 10%. Okay? Then we compute 1000 times 10% gives us 100, meaning to say our sodium hydroxide weighs 100 grams. How come that our our unit becomes gram? Remember that this percent is weight per volume. Okay? Then we can cancel ml, ml, and the remaining unit is the weight of our solute, which in this case is 100 grams. Now, in order for you to make 10% of 100 ml solution of sodium hydroxide, you have to weigh 100 grams of sodium hydroxide to be added in 1000 ml solution or 1000 ml solvent, which will give you a percent concentration of 10%. But remember, sodium hydroxide diluted in water will give an exothermic reaction, which means there will be a production of heat. Okay? Next example is make up 50 ml of a 2% volume per volume concentrated hydrochloric acid. So how are we going to compute for this one? We are asked to compute, or we are asked to solve or prepare 50 ml of 2% volume per volume concentrated hydrochloric acid. Okay, so again, we have here percent concentration, volume per volume is equals to volume of solute over volume of solvent. Okay, again, our given are 2% volume per volume and 50 ml solution or 50 ml volume. So how are we going to do that? We have here 2%, okay, is equals to x over 50 ml. So basically the same thing. But instead of looking for the mass, we are now looking for the volume of our solute. So x is equals to 50 ml times 2%. 50 times 0.02 will give you 1. Again, 50 times 0.02 will give you 1. So we need 1 ml of concentrated hydrochloric acid to be added in 50 ml solvent to make a solution with a concentration of 2% volume per volume. Meaning to say, every 50 ml of this solution contains 1 ml of concentrated hydrochloric acid. Next problem that we have is this, molarity. Now, what do we mean by molarity? Molarity is routinely expressed in units of mole per liter, or sometimes it can be expressed as millimoles per milliliter. Remember, molarity is the amount of moles per 1 liter of solution. Let's have an example. How many grams are needed to make 1 liter of 2 molar solution of hydrochloric acid? Again, we are asked to compute for how many grams are needed to make 2 ml of 2 molar solution of hydrochloric acid. So how are we going to solve for that? We said that moles is equals to molarity rather. Molarity is equals to moles per volume. And remember, the volume must be expressed in liters. If you're going to recall your inorganic chemistry or your MLS 103, okay, we know that moles can be computed by using the mass over molar mass. Okay, the mass over molar mass. So aside from moles is equals to molarity rather, aside from molarity is equals to moles per volume in liter, we can compute it using molarity is equals to mass, okay, molarity is equals to mass time over molar mass times volume in liters. So aside from molarity is equals to moles over volume in liter, we can say that molarity is equals to mass over molar mass times volume in liters. Now, using this formula, how are we going to solve for this one? The step one is we need units are needed to the final answer, and that will be grams per liter. Okay, uh, we have here, or we are going to get the molar mass of our solution of our HCl. So we have here HCl. L is 35.45. Hydrogen is 1.01. Those are their atomic weight times 1 times 1. 35.45 times 1 is equals to 35.45. 1.01 times 1 is definitely 1.01. Then we get the sum of this, which is equivalent to 36.46 grams per mole. So this is our molar mass. So, assuming that we are going to look for the mass, how are we going to solve for that? Again, our molarity is 2, the volume is 1 liter. So how are we going to do that? 2 molar is equals to X, which is the mass, over 36.46 grams per mole times 1 liter. So we are going to multiply both sides by this one. So we have here X is equals to 2 molar, okay, over 36.46 grams per mole liter. Remember that this is expressed as mole per liter. We can cancel this, we are left with grams. Therefore, this will be 2, okay? I'm sorry, this is incorrect. I'm sleepy. Sorry guys, just a human being. So how are we going to do that? We have here X is equals to 2 molar times 36.46 grams per mole liter. So again, remember this one is expressed as a mole per liter. So mole, liter, liter. Therefore, we have 36.46 times 2 will give you 72.92. X is equals to 72.92 grams. So this is the amount of our hydrochloric acid needed in order to prepare 2 molar solution with a volume of 1 liter. Okay? Next, how to prepare 250 ml of 4.8 solution of acetic acid. Again, how to prepare a 250 ml of a solution of 4.8 solution, a molar solution of acetic acid. So how are we going to compute for this one? What is the formula that we are going to use? We are going to use the molarity is equals to moles divided by volume per liter. So okay, we have moles, molarity is equals to moles over your volume in liter. So what is our molarity? The molarity is 4.8. Molarity is 4.8. Volume is 250 ml. 250 ml. Remember, the volume must be expressed in liters. So we have to convert 250 into liters, which will give us 250 times 1 liter is equals to 1000 ml. Cancel, cancel. We have 250 divided by 1000 is equivalent to 0.25. 0.25 liters. Okay, we are going to get the value of our solution. So we have, let me delete it first. So we have 4.8 molar is equals to moles over 0.25 liters. So we have moles is equals to 4.8 molar times 0.25 liters. Again, remember this one is equivalent to moles per liter. Cancel liter, cancel liter. So the number of moles is 4, 4.8 multiplied to 0.25 will give us 1.2 moles. 1.2 moles. Now, in order for us to get the mass, no? In order for us to get the mass of the solution or the volume of the solution of your acetic acid, sorry, so we have to convert this into grams. So how are we going to do that? By simply multiplying this to the molecular weight. So, what will be the molecular weight of acetic acid? Remember that acetic acid, the chemical formula of acetic acid is CH3COOH. Okay? This is also known as the ethanoic acid or an example of carboxylic acid. Remember that the molar mass of acetic acid is 60.05 grams per mole. Okay? So we have to multiply it. 1.2 moles 1.2 moles times 60.05 grams per mole. Cancel moles, cancel moles. So we have 60.05 times 1.2 will give us 72.06. Okay, this will give us 72.06 grams. So this is the amount of the acetic acid needed to prepare 4.8 molar solution. But if you want to get the volume of this one, the volume of 72.06 grams of acetic acid, then we have to multiply it to its density, okay, in order to get the volume. And the density of acetic acid is equals to 1.05 grams per ml. Okay, remember, density is equals to mass over volume. If you're going to get the volume, then volume is equals to mass over density. Therefore, applying the formula, no, applying the formula 72.06 grams over 1.05 grams per ml will give us 72 0.06 divided by 1.05. This will be equal to 68.63 ml. In other words, to prepare a solution with 4.8 molarity, we have to measure 68.63 ml of our solution. Okay, 68.63 ml of our acetic acid. How about this one? Normality. What is normality? When we said normality, it is equivalent to the expression or expressed as number of equivalent weights per liter or milliequivalents per milliliter. In this question, we have what is the normality of a 500 ml solution that contains 7 grams of sulfuric acid? Again, what is the normality of a solution, no, whose volume is 500 ml and contains 7 grams of sulfuric acid? So how are we going to solve for that? Again, remember, normality is defined as number of equivalents per liter or milliequivalents per liter. So how are we going to solve for this one? So we have 7 grams of sulfuric acid over 500 ml multiplied to 1 equivalents over 49 gram sulfuric acid, okay, times 1000 ml over 1 liter. Cancel ml, cancel ml, cancel grams, cancel grams. The question is, where did we get 49? Remember, there are 49 grams per equivalent of our sulfuric acid. This will give us 0.285 EQ over liter, or simply equivalent to 0.285 normal. So that's how we're going to compute for our normality. Oh, I'm sorry. I failed to share my whiteboard. So that is the okay. Again, so we have 7 grams of sulfuric acid divided by 500 ml times 1 EQ over 49 grams sulfuric acid times 1000 ml over 1 liter. Okay, cancel all the same uh, unit, and it will leave us, or the units left are equivalents per liter. Okay, then the answer is 0.285 EQ per liter, or equivalent to 0.285 normal. Next is density and specific gravity. Remember, people, that density is defined as the ratio of mass per volume. And when we set specific gravity, that is the ratio of density of a certain substance compared to the density of water. We all know what is the density of water, right? The density of water is 1 gram per ml. Remember, when we said specific gravity, there is no unit for that. Example, what is the actual weight of a supply of concentrated hydrochloric acid whose labels reads 1.19 specific gravity? Again, what is the actual weight of a supply whose uh, label reads specific gravity 1.19? Okay. Ah, I think my problem is incomplete. Okay, with a specific gravity of 1.19 and an assay value of 37%. Please include that. What is the actual weight of a supply of concentrated sulfuric acid as hydrochloric acid whose label reads specific gravity of 1.19 and an assay value of 37%. So how are we going to solve for that? We have 1 gram, 1.19 gram per ml. Oh, sorry, wait. Where did we get 1.19 gram per ml given that the specific gravity of the solution is 1.19? Why did we come up with gram per ml? Remember, as we define specific gravity, that's simply the density of your solution times the density of divided by the density of your water. So, in other words, it's just the same. No, I just remove the unit. This will be multiplied to the acid value, which is 37%. Okay, which will give you 0.44 grams per ml of hydrochloric acid. So that will be the answer. That will be the actual weight of our concentrated acid. Next is convert 5 milliequivalents to liter of sodium to millimoles per liter. Okay? We are asked to convert 5 millimoles of sodium to milliequivalents per liter of sodium to millimoles per liter. Remember guys that the conversion factor for MEQL, no, the conversion factor for MEQL to millimole per liter is 1. So this is basically the same, no? So 5 MEQL per liter is equivalent to 1 millimole per liter. But 5 millimole per liter of sodium is dangerous, no? Sobrang baba ng kanyang sodium level. Okay? Next problem is, you are the medical technologist on duty in the clinical chemistry section. The unit of your chemistry analyzer is set at conventional unit. The doctor requested you to report your results to SI or International System. BUN is 12.5 grams per deciliter, and you have to convert it into millimoles per liter. Creatinine is 0.85 milligrams per deciliter. And again, you have to convert it into millimoles per liter. So how are we going to solve for that? What is the formula? Remember, In clinical chemistry section, we have what we call conversion factors. And these conversion factors will help us, no? And these conversion factors will help us to solve, to convert our conventional units to system or international units or SI. So remember, if we have to convert BUN or urea nitrogen or urea, no, to from milligrams per deciliter to millimoles per liter, our conversion factor is 0.357. Please take note. If we are going to convert BUN from milligrams per deciliter to millimole per liter, then our conversion factor is 0.357. Given that our BUN value is 12.5 mg per dl and you have to convert it to millimole per liter, so we have to multiply, no? Multiply 12.5 to 0.357. So 12.5 times 0.357, okay? So 12.5 times 0.357 will give you 4.46. This is equivalent to 4.46 millimole per liter. In other words, 12.5 mg per dl of your BUN is equivalent to 4.46 millimole per liter. Now how about for creatinine? For creatinine, no, from milligrams to deciliter, from milligrams per deciliter to millimole per liter, then our conversion factor is 88.4. In our problem, we have 0.85 milligrams per deciliter of our creatinine. Then we have to multiply it to 88.4 as our conversion factor. So 0.85 times 88.4, okay? 0.85 times 88.4 will give you 75.14. 75.14 millimole per liter. So those are the ways on how we are going to convert our unit from conventional to our international units. This time, you are not converting anymore kilometer to meters and vice versa, Kelvin to Celsius, Celsius to Fahrenheit, but you are going to convert it, no, the unit of your acid value. Now, the question is, do we have to remember or do we need to remember our conversion factors? Yes, you have to remember your conversion factors because that is important. I'm going to upload the conversion factors in our learning management system so that you will be guided on how to convert conventional unit to SI unit. This will be the end of our second lecture. I hope I was able to recall your concepts in molarity, normality, and percent concentration. Please pardon me if I can share myself to you at this point in time. I am recording this video at 3 in the morning, 3 a.m. So please, medyo haggard na po si sir, kaya po hindi na po nakapagpakita sa inyo. Babawi na lang po sa susunod na video lecture. Okay? So I have uploaded sample problems in our learning management system. I am expecting that you will be able to solve for that and you will be able to get the correct answer. Once again, thank you for listening. Sorry for my soft voice in this lecture because I can't make it loud. The time check is 3 in the morning. Thank you and I hope you will learn.